One great characteristic of mathematics is the ability for chaos and complexity to arise out of the simplest of parameters. This video is about a topic known as percolation, or percolation theory. To understand the complexities of percolation, I'm going to use an analogy, so let's set it up. Imagine a square grid of points which extends forever in every direction. Each point can be connected to its four neighbors on the north, east, south, and west. If 2 points are connected, we'll call this connection open, and if they're not, we'll call it closed. Now let's make a variable p, which is the probability that any connection will be open. If p equals 1, there's a 100% chance of each connection being open, so all of them are. If p equals 0, none are open, as the probability is 0%. Now let's imagine that each point is an individual, and each open connection is a friendship. Now, since our open connections are friendships, let's say that a certain point wants to throw a party. This person invites their friends and tells them each to invite all their friends and to give them the same instructions. If the probability of friendship is 1, the invitation would travel as far as the infinite grid extends. This would mean that an infinite number of people would attend the party. This is great because every person would get to go to a party, but let's say that we want to avoid scenarios such as this. If p equals 1, we can connect any 2 people in this infinite grid through friends of friends and so on, no matter how far apart they are. But if p was a lower number, that wouldn't necessarily be possible. Now let's say that if we can connect 2 points, no matter how far apart they are, that they're in the same party or region. Now, say that we want every individual to be able to go to a party, but we don't want any infinite parties. It's fine if there are some of just 1 or even 1 billion, just as long as they have a finite number of partiers. To do this, we'll have to change the friendship probability p. We already know that for some values of p, such as 1, there will be at least one infinite party. We also know that it's possible for scenarios with no infinite parties, such as p equals 0. The study of percolation theory is what tells us about the area in the middle. Ultimately, what percolation theory tells us is that for a p-value greater than or equal to 0.5, or 50%, an infinite party is not only possible, but guaranteed. Additionally, for values less than 0.5, an infinite party will not occur. This probability is therefore known as the critical point, because it's the transition point at which an infinite region, or party, splits into many finite regions. And percolation is something that intrigues me to no end. Its simplicity yields complex, interesting results, and it has applications within mathematics, but also reaching into the real world, from the structure of coal, where percolation theory has its beginnings, to modern research in ecological habitat destruction. Finally, I just want to say thank you for watching. One of my hopes with this project is that these videos will help foster an interest in mathematics in people of all levels of expertise, so I thank you for being a part of that.